Hello all, I'm Sashikiran Reddy from Group 24 CSE 535 Mobile Computing. Today I'm going to present our Project 3 Vision. It is a multi-modal sensor fusion framework for infrastructure-free indoor navigation for the visually impaired. This is the information of our group members, and today we are going to cover all these topics related to our project in this presentation. Coming to the introduction. Over 285 million people worldwide face significant challenges navigating unfamiliar indoor spaces. While GPS has revolutionized outdoor navigation, it falls short inside buildings. Indoor navigation systems often rely on costly physical infrastructure like Bluetooth beacons or require labor intensive manual mapping, which limits accessibility and scalability. And how does Vision address this? Vision aims to overcome these challenges by leveraging modern smartphone capabilities, on-device AI, and sensor fusion to provide real-time, accurate, and intuitive navigation for visually impaired users. Coming to the related study, we have gone through many papers related to this domain, and we have compared our approach to the current existing models or approaches. And we have classified several features to actually compare our approach with the other models. The features include infrastructure, primary tech, scalability, key limitations, and the guidance or output form. Coming to the infrastructure, Vision does not require any infrastructure because it's inbuilt in the smartphone which we use. Whereas other models such as QR/AR markers, BLE UWB beacons, inertial dead reckoning, general object recognizers, VIB mobile service, or visual recognition apps or assist model actually requires while not all of them requires physical infrastructure, but many of them requires manual placement of visual markers or requires installation and maintenance of beacons, or it also requires BLE installation at the places. Whereas primary technology involved in vision is VIO or SLAM, AI object recognition or sensor fusion. Whereas in other approaches, computer vision, radio trilateration, IMU sensors or machine learning models are used. Coming to the scalability, Vision tops of all approaches because Vision does not require any physical infrastructure rather than the smartphone we use, whereas other markers are very hard to scale or mediumly scale. Coming to the key limitations, the only key limitations in the Vision is it's computationally expensive or intensive, and it has potential drift, whereas other approaches has there are certain limitations such as some requires line of sight, markers can be damaged, high cost, battery maintenance is required, some may accumulate severe errors in drift, and some does not have localization, some are not used, some cannot be used for navigation, and also some has uh, opt, uh, lightning sensitive and some offlinely compute limits, and BLE signals has some noise. So there are certain limitations with all the approaches. And when compared to Vision does not have except for the computationally intensive, and sometimes there may be potential drift, which we also address this issue. Coming to the guidance signal, almost every model as along with the Vision as it's the same, it's the spatial audio haptics or semantic cues. We also studied several other papers, like we have studied, which is more closest to our approach, which is RNF safety-centric navigation. But our approach actually differs from this because our approach is totally a totally operates entirely on commodity consumer smartphones, whereas RNF is totally related to robotics and uses industrial grade sensors such as LiDAR. Uh, and while we are reading these papers, we came to know that BVI community is broadly categorized into two categories: infrastructure dependent and infrastructure free, where the our model comes under infrastructure free approaches. And we also studied several other models which uses VIO SLAM, but there is one important problem, which is the drift accumulation, which we actually address these gaps by by solving the drift problem of vision-based systems using the strategic fusion of VIO SLAM with ambient RF signals. Questions answered. Q. Question one, why is it important to solve the problem? So navigating indoor environments independently is not just a convenience. It is essential for accessing education, employment, healthcare, and community life. So our vision helps visually impaired to actually use it, and they can be independent and totally self-reliant. Question two, how is this problem related to mobile computing? While this problem can be solved using other approaches, we think that mobile computing is the best approach to solve the problems for the visually impaired, because vision is totally used on the smartphone we use. Today, many smartphones like Google Pixel 8, iPhone 15, Samsung Galaxy S24 has very high level chips, contains high level sensors which can do very intensive computations, and also very intensive computations, and also it contains sensor which support to actually solve the problem of the visually impaired. And some models can also do on-device machine learning, effective VIO, SLAM, and also non-visual interfaces using spatial audio haptics can be derived from this input. What makes your proposed solution novel or unique? Vision is a mobile application that integrates three main technological pillars: visual, inertial odometry, VIO, ambient signal correction, and semantic topological mapping. The core navigation engine uses VIO, which uses camera and the IMU data, which are already present in the smartphone, to track user motion in real time. To correct cumulative drift inherent in VIO over longer distances, Vision incorporates ambient signals such as Wi-Fi, round-trip measurements, and detectable Bluetooth beacons. This opportunistic sensor fusion ensures precise localization without requiring any physical infrastructure. Is our solution technically sound and feasible? Yes, our solution is technically feasible because, as we discussed earlier, smartphones today already include all necessary hardware and software. Devices like Google Pixel 8 or iPhone 17 or Samsung contains all the sensors and all the chips which required for our computation already present in them. So it's very easily scalable and technically feasible too. And what is the 5-year plan? So the 5-year plan of Vision is, year one, we focus on foundational research algorithm development, and year two, we emphasize prototype development and control user studies. And in the year three, I'm sorry, in the year three, Vision is used to recognize semantic understanding and dynamic environments, and we focus shift on improving the system semantic intelligence. In the year four, involves scalability and robustness and testing in large and complex environments. And finally, year five culminates all this in the public release and research on the next generation features such as AR smart glasses integration while ensuring usability, safety, and reliability. System architecture and methodology. So coming to the system architecture and methodology, Vision is built on modular and service-oriented architecture. The system contains of three primary modules: sensing and data acquisition, core processing, and user interaction. The sensing and data acquisition model collects input from the smartphone camera, IMU sensors, and optional ambient signals such as Wi-Fi RTT. BLE Bluetooth is beacons is a optional feature. So they collect data from all this and it sends to the data pre-processing layer, and this raw sensory data is pre-processed and synchronized to ensure accurate fusion. And the core processing module handles the drift correction. Here, the VIO engine tracks motion while ambient signals correct positional drift, and simultaneously, lightweight AI models perform object and landmark recognition to dynamically build a semantic map. And the modular design allows updates without actually, disturbing the rest of the system. And these signals are sent to the multimodal guidance engine, and they are converted into spatial audio or haptic feedback, which are required by the users. And we also have the optional cloud layer where we can integrate this to solve some scalability or computational issues. And so optional cloud services can centralize machine learning model training, collect usage data, and distribute semantic maps across devices. Heavy computational tasks can be offloaded to servers, ensuring smooth and real-time navigation. Now coming to the evolution methods. Uh, The systems will be evaluated on localization, accuracy, drift management, frame processing speed, and response latency. And coming to the ethical considerations, include privacy protection, secure data storage, and safe navigation to prevent hazards. And vision ensures fairness and inclusive access for all users while preventing unauthorized mapping or misuse of sensitive spaces. User study and testing framework. User studies will measure usability, clarity of instructions, and confidence in safety, which will be required for the development of vision. Coming to the conclusion, vision represents a significant advancement in assistive technology for the visual impaired. By providing infrastructure-free real-time indoor navigation using widely available mobile devices, vision removes barriers to independence, self-reliance, and vision has the potential to transform indoor navigation for millions of users worldwide. And these are the contributions listed in our PPT. And thank you.